Hello everyone, I'm Chris McIntosh and I help teach some of the statistics courses. And this week I wanted to hit some of the highlights in Navarro's chapter on comparing two means. The material I'm covering here comes from chapter 11, comparing two means, and from chapter 16, Bayesian statistics. So Navarro first talks a bit about the one sample z-test. And it's comparing the mean when the population standard deviation is known, and Navarro makes the point that this text is never used. I've never seen it used or published because we really never know the true population standard deviation. It's just a test that's usually used for testing purposes. So we'll just move on from there. You don't need to know much about that one. The first one that Navarro covers is the one sample t-test, and that's when you want to compare the mean of a sample to a known value, and you're going to estimate the standard deviation using the sample standard deviation. And because the standard deviation is estimated from the sample standard deviation, a t-distribution is used instead of a z-distribution. And the difference between those is at lower degrees of freedom, the t-distribution has heavier tails than the z-distribution. The test statistic is a t-statistic, and the degrees of freedom is the number of observations minus 1. And we're going to get down to, we're going to move on from this because usually we're more interested in comparing the means of a couple different samples instead of just one sample. So the independent t-test compares the means of two different samples. It's used when you have a continuous dependent variable and a dichotomous independent variable. Dichotomous means you have two groups. Sometimes a one-sided independent t-test is used, and that is when you think that there's a specific direction in the difference. And I don't usually recommend you use one-sided t-test. Sometimes people use it to increase their power. If they hypothesize that a difference is positive or negative specifically, they will move all of their type 1 error rate to one side and might detect a difference a little more easily. And I don't usually recommend that. So usually we just look for a difference and not using a one-sided test. There are assumptions with the independent t-test, and the assumptions are that the data are normally distributed, observations are independent. There's an assumption called homogeneity variance, and all that really means is that the standard deviation for the two samples are equal to each other or close to equal to each other. We're going to talk a little bit more about that. And this is an important assumption for all statistical tests. It wasn't really mentioned in the texts, but I'm going to go ahead and include it here because you really should be considering this an assumption of statistical tests. And the assumption is that samples are randomly selected from the population. So to the extent that you randomly selected from a population to make up your sample, then your p-value is accurate. But when things are not randomly selected, then these p-values start being off because you're not using random processes to do the selecting of the data. So this is something to keep in mind when you're trying to interpret results and know how they apply to your research question. The statistical hypotheses for an independent t-test, the null hypothesis H0 is there is no difference between group means, and the alternative hypothesis, or H1, is there is a difference between group means. The degrees of freedom for an independent t-test is the number of observations minus 2, because you have two groups here. And the confidence interval that's reported with an independent t-test is for the difference between the two means. So you take the mean from one group and subtract the mean from the other group, and that's what the confidence interval is reporting. The effect size, the most common one used, is one called Cohen's d, and the interpretation for Cohen's d around 0.2 or less is considered a small effect size. Moderate is from 0.2 to around 0.5 or 0.6, and above and then up around 0.8 is what's considered a large effect size. And I gave you the format for the reporting a t statistics in a research report there on the slide. You want to report the degrees of freedom, the value for the t statistic, the value for the p value, and your Cohen's d value. You want to check your test assumptions before interpreting it. So to check the normality assumption, I learned what was called by my instructor an eyeball test, which was basically just checking the histogram. Does the histogram look like it would be fairly close to normally distributed, or are there obvious outliers in there? You can get a pretty good idea just by looking at the plot. So that's always a great place to start. Navarro does mention a QQ plot, which simply lets you see how the data compare to a normal distribution. You'll see there's a diagonal line on there, and then the points of the data and how well they line up on that diagonal line. When it looks like this means it's fairly well normally distributed, but when a lot of data points start to deviate from that line, then you know you might have an issue with normality. There is, besides looking at plots and just kind of making a judgment call, there are some actual statistical tests to check if things follow a normal distribution. And the one mentioned in the Navarro text is called the Shapiro-Wilk test. But I thought I would mention to you, there's another one that I actually learned about when I was a student called the Kolmogorov-Smirnov test. They both test for normality. They use some slightly different procedures. But if the test is significant, then it means that your data deviate from normality. There's a significant difference from normality. But in reality, when it comes to a normality assumption, like all things in statistics, it's kind of, there's a lot of shades of gray here. Skewness is a lot more important than kurtosis. So sometimes the Shapiro-Wilk and the Kolmogorov-Smirnov test will be significant, meaning something deviates from normality, but those can both be impacted by the kurtosis of the distribution as well as the skew, and in reality the kurtosis isn't such a big deal. So sometimes you can just look at the skewness divided by the standard error of the skewness, and if you start getting skewness divided by standard error of the skewness greater than a value of 2, then you might have a problem with your normality assumption. And again, if a lot of this is more important if you have a small sample size. So if you have a large sample size, 30 and above, the normality assumption gets a little less important, and you can use the t-test even if your data aren't really close to normal when you have large sample sizes. The other assumption that you check is called homogeneity variance. And like we noted, the homogeneity variance is looking to see if the standard deviations in the two groups are close to each other. And there's actually statistical tests that you run called Levene's test. And that test, for if the variance between the distribution between the two samples is the same, you want this test to not be significant. So this one's a little backwards from what we're used to looking for. We're usually looking for a significant result. And in this case, we don't want there to be a big difference. So we're looking for a non-significant result or a large p-value for Levene's test. So there are some options to consider if you violate your t-test assumptions. If the data are not normally distributed, like I mentioned already, if you have a large sample size, it may not matter too much. But if you don't have a large sample size, the sample size is small, and then you're not normally distributed, you should probably consider doing a non-parametric test instead. And the non-parametric equivalent of an independent t-test is called the Mann-Whitney U test. And there is something else called robust methods that can be used when you have assumption problems. For the homogeneity variance test, there is an adaptation of the student t-test called the Welch's t-test, and most statistical programs will give you both, and you just need to decide, do I interpret the regular student t-test results, or do I interpret the Welch's t-test results? If you do not have a significant Levine's test, then you can interpret the normal student t-test results, but if it is significant, then you should interpret the Welch's t-test results instead. And we'll see what those look like when we get to the computer assignment. I talked before about the example Navarro gave for reporting results, and Navarro gave just this pattern of describe some descriptive statistics for the reader so they can get oriented to the data, describe the test used and what was being tested, what's the null hypothesis. You report relevant statistical information. Well, I need to fix that slide and see the previous slide for that, and I'll fix that before I post it, and then interpret the results for the reader. And I gave you an example description of some reporting right there. And some extra information about effect sizes. There are different effect sizes used for different statistical tests. We've seen the Kramer's V for chi-square test, and now Cohen's D for this independent t-test. But also be aware there are other effect sizes sometimes for the same test. And we try to focus on what's most common. For t-tests, Cohen's D is the most common test by far, but there are others that you might see. I've seen eta squared used before. I've seen omega squared used before. So just be aware that there's other effect sizes that might be reported. And sometimes you just, if you don't recognize an effect size, go Google it and see what it is and how to interpret it. So don't be surprised if you see that in some publications sometimes. So Navarro in their text mentions Bayesian statistics, and I've had you read part of chapter 16 on Bayesian statistics and the part that talks about Bayesian hypothesis tests, because I want you to be aware that there is an alternative out there, and the tools to use Bayesian statistics were not widely available in the past, but they're becoming more readily available, and they're not too hard to use. And so I wanted to go ahead and expose you to this idea, and I'm going to add one more concept into what we're looking about with the tests that we look at this semester, and that concept is the Bayes factor. And Bayesian statistics are about updating our beliefs. What do we believe is true? And so part of that is calculating probabilities of things. And as you skim through the chapter, you'll see the math is a little bit complicated. You don't need to focus on the math. I'm not going to do a lot of math. But we are going to look at something called the Bayes factor. And what the Bayes factor is an odds ratio comparing the probability of the null hypothesis being true against the probability of the alternative hypothesis being true. And Navarro recommends writing it as a whole number, not a fraction. And you'll see this reported as a capital B, capital F, a 0, 1, meaning that that's supporting the null hypothesis, or you'll see it written as a BF10 as supporting the alternative hypothesis. And we'll look at what that looks like when we get to the computer assignment. And like I said, the tools to calculate it are easy. And what I like about the Bayes factor is it kind of gives us an idea of how strong is our evidence for what we're looking at. Sometimes I think some studies overstate the strength of their evidence in whatever they're trying to show. And this gives us a way to kind of gauge that strength a little bit. So I think it's good to understand what this is. And if a Bayes factor falls between 1 and 3, the guideline, and these are loose guidelines, is that's kind of negligible evidence. supporting a hypothesis. And if the base factor is between 3 and 20, it's probably kind of modest evidence. 20 to 150 would be kind of strong evidence, and greater than 150 would be considered very strong evidence. So, and this actually does provide evidence to support a hypothesis, and this is quite different than how we think about null hypothesis significance testing. So I want to introduce you to this concept and use it a little bit this semester. So you see this way. You'll probably very rarely see it reported, but tools are becoming more available. So I wanted to introduce you to it in case you do see it somewhere, or you want to use it yourself, because I think it is a useful tool. And we will go over the steps of null hypothesis significance testing for the independent t-test in our computer assignment. And that's it for this lecture. Talk to you later.